Hi, let us solve together this problem. They say assume that a 50-kilogram runner trips and falls on his extended hand. If the bones of one arm absorb all the kinetic energy, so we don't consider the energy due to the fall, what is the minimum speed of the runner that will cause a fracture of the arm bone? Assume that the length of the arm is 1 meter and that the area of the bone is 4 centimeters square, what is basically the same that 4 times 10 to the negative 4 meters square. So what happens here? There is a guy that is running, fall, and he's falling on his extended hand. So all this kinetic energy, will be absorbed by the bone. Now, if we want to find the minimum speed that will cause a fracture of the arm bone, we have to say that this kinetic energy will be equal to the energy absorbed by the bone at the point of compressive fracture. So this is something that we have explained in the previous exercise. So this Ke here is the kinetic energy that is depending on the speed of the guy that is running and his mass, right? And here we have the energy absorbed by the bone at the point of compressive fracture. So what is kinetic energy is 1 over 2 mass times the square of the velocity, or the square of the speed of the guy that is running. And this is equal to what is the energy absorbed by the bone at the point of compressive fracture is 1 over 2 times the area times the length of the bone times the breaking stress of the bone divided by the modulus of G. So of course 1 over 2 and 1 over 2 cancel out here. So we have that B squared is equal to A times L times breaking stress of the bone square over the mass times the modulus of G. So applying the square root to both sides, we have that the speed, and you remember that this speed we are calculating here will be the minimum speed of the runner that will cause a fracture of the arm bone. So any speed above this number is also going to be cause of a fracture of the arm bone. So this is the square root of A times L times the breaking stress of the bone square over the mass of the person times the modulus of G. If we substitute now here, we have that the speed, of the runner will be equal to what is the area? 4 times 10 to the negative 4 meters squared times what is the length of the arm? 1 meter times what is the breaking stress of the bone? 10 to the 8 pascals. Pascals is equal to newtons over meter square. But this is a square all over the mass that is 50 kilograms times uh, the modulus of June, the for the bone is 14 times 10 to the 9 Pascal, so Newton over meter square. Let us make a very quick analysis of the units. This is always very important because this let us understand if we are working with the correct units, if our formula is okay, is correct. So what we have here, we have meter squares that are coming from the area. We have these meters that are coming from the length of the arm. We have Newton over meter squared square. So when you square a Newton, you get Newton square. When you square a meter squared, you get meter to the fourth power. And below you have these kilograms, and you have Newton over meter squared. So I will flip and multiply. I get meter squared times meter times Newton squared over meter to the fourth power times, then when I flip, I get meter squared on the top, and I am dividing by kilograms Newton. So now we're going to simplify. So meter squared times meter squared would be meter to the fourth. So meter squared times meter squared can be canceled with this meter to the fourth here below. Now we're going to cancel out these newtons, with one of the newtons I have over here. So what I have meter times newton over kilogram. This is meter times what is Newton? Newton is kilogram meter per second square all over kilogram. We're going to simplify the kilograms, so we have meter times meter, that is meter square over second square. Perfect, because these are the units that I'm going to get under the radical. So if I find the square root of meter square over second square, this would be meter per second. That is the unit of speed, right? So my calculation will be correct. So if now we multiply 4 times 1 and we divide by 50 and we divide by 14, we're going to get 0.00571 times, and then let us see the powers of 10 we have here. So we have 10 to the negative 4, we have 10 to the 8 squared, that is 10 to the 16, and we have this 10 to the 9 that becomes 10 to the negative 9, and then we have the units meter squared over second squared. So of course, these 10 to the negative 4 times 10 to the negative 9 is 10 to the negative 13, 10 to the negative 13 times 10 to the 16 is 10 to the third, and 10 to the third power times 0.00571, it will be a square root of 5.71 meter squared over second square, right? So when we find this square root, we're going to get this is 2.39 meters per second. So the minimum speed of the runner that is falling on his extended arm to fracture its arm will be equal to 2.39 meters per second. Speeds lower than 2.39 meters per second, for the speeds lower than 2.39 meters per second, the amount of energy that is absorbed by the bone is not enough to fracture the bone. For speeds higher than 2.39 meters per second, the amount of energy that is absorbed by the bone would be higher than the maximum energy, that can absorb the bone without fracture. So for speeds higher than that, we have a fracture of the bone of the arm. For speeds lower than that, we're going to have that probably there will be no fracture in the arm of the person that was running. So this is basically how we solve this exercise.